Okay, we're going to talk about completely randomized designs, the simplest and most fundamental model that we'll take a look at in this course. Most of you will have seen this before, so think of this as a review. And also, though, making sure you really understand the basic issues, because this is really a foundation for every other design that we'll be looking at throughout the course. So when we talk about a completely randomized design, acronym CRD, we're talking about design with big N units, G different treatment levels. The sizes are N1 up to NG, and the treatments are randomly assigned to the units. So this complete random assignment means that every possible grouping of units into G groups is equally likely. So we're not using any control over types of allocation of or assignment of treatment groups to the observations. We are doing something that is completely random and every possible configuration is equally likely. Very large set of assumptions, but one that applies a lot of the time. And let's talk about cases where this is perfectly reasonable. This is, like I said, the most basic design, and everything else is kind of based upon this. It's the easiest to do, easiest to analyze, most resilient when things go awry, and is often what we should do. Okay, so let's think of some cases like this. Does a wood board 0.625 inches thick have the same strength as a 0.75 inch thick board with a notch cut to 0.625 thickness? So they took 26 2.5 foot boards, by 3 foot boards, or 2.5 inches by 3 foot boards. Sorry, I read that wrong. Half are chosen to be notched at the center. So a random assignment of the treatment, and the response load at failure with horizontal bending. Okay, so notice we randomly assigned that notching the treatment, and then we measure. So 2 levels, either notched or not. Here's another scenario. Do the efflux transporters PGP and BCRP affect the ability of a certain chemotherapy drug to cross the blood-brain barrier? We'll make 30 in vitro measures of the chemo accumulation in cells. 10 will be done with wild type. So here we've got our levels. So 10 done with wild type, 10 with cells that have overexpressed PGP, and 10 with cells with overexpressed BCRP. The transporters are randomly assigned to the trials. So again, 3 levels in this case, randomly assigned completely. Does xanthan gum and or cinnamon affect sensory quality of gluten-free cookies? 8 batches of cookies will be made. Remember, a batch is just a batch, has multiple cookies in it. With 2 of the 8 batches assigned to each of the 4 combinations of low versus high gum and low versus high cinnamon. The response is a sensory score. Okay, so notice here we've got 4 combinations. We could have low, 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 high, high, low, or high, high for the gum and cinnamon content, and that is completely randomly assigned to the responses. So number 4, how do sling length and size of counterweight affect the throw distance of a trebuchet, I think is how you say that. What am I talking about? I'm not even sure, so let's look at the next slide. This is a trebuchet, as I think it's pronounced. So notice we have the throwing arm, the base, the sling, the counterweight, the trigger, where you pull the rope and have it sling. It looks something like those are some really big trebuchet. I'm probably so wrong about that pronunciation, but it sounds like it should be French, right? So let's go back and read the problem now that I kind of know what I'm talking about. We have a random assignment of 27 throws to the 9 combinations of 3 lengths and 3 weights. So that's 3 times 3 give you 9 treatment levels. This is a factorial design that we'll talk about later in the course. The response is the distance of the projectile. So we want to find which combination of length and weight gives you the maximum distance. Maybe you want minimum distance, I don't know. But the point is that these levels are randomly assigned to all the different throws. Okay, so our inference is going to be about the means in each one of those 4 scenarios, and we want evidence. Are the means the same, or is there evidence that they're not all the same? If so, which ones differ? And is there a discernible pattern that will give us a parsimonious explanation of how they differ? Any kind of pattern we can detect. And how can we describe that pattern in a nice, succinct, parsimonious way? And then we want to produce estimates and or confidence intervals of those means or differences. Variability may be of interest in certain cases especially when we start getting deeper into the course. We'll think more deeply about variability. So we want the simplest model. I know we like to entertain complex models at times just for fun, but we need to recognize that if a simple model works, we should use it, right? So all treatments have the same mean is a simpler model than each treatment has its own mean. And if we don't have evidence that each treatment needs its own mean, why not just say all treatments have the same mean, okay? So we have an inclination toward the simple model. And sometimes we seek a model that explains things. So we may be able to find evidence that the treatment means vary linearly with temperature. So we see as the temperature raises, the means increase or decrease systematically. That's a good explanatory model that we want to be able to report when that is true. We may also be able to say that they quadratically vary with temperature. That often is the case. And we'll learn how to fit those kinds. Famous quote that I think comes up in every course I teach of applied statistics is all of the models we will entertain this semester, George Box would say, are wrong. But some of them work pretty well. So he said all models are wrong, some models are useful. We don't need the model to be theoretically perfect in terms of like, if we see a quadratic curve fits the data, but we know if we extrapolate beyond our range of observed data points that it's probably not going to behave in a quadratic way, I'm not that concerned because we're going to pick the model that the data is consistent with for the data we have collected. Okay. Sometimes if you're from more of a math background, people take issue with that, but we do what works and what provides a simple explanation of data, as in statistics. We're going to gauge model fit by looking at sum of squared residuals. These are measures of variation. Hence, we use the analysis of variance to help us make decisions about our model. When we have the choice, we choose model parameters that minimize the sum of squared residuals. So let's take a look at this sum of square equality here at the bottom of the slide. The total sum of squares is all of the variation in all of the response data. Okay, the sum of squares M is the explained sum of squares, and sum of squares E is the error sum or residual sum of squares. For a fixed set of data, if you change the model to make one of these, either the M or the E bigger, the other one has to get smaller because it's going to just equal total sum of squares. So that's what we're stuck with. We're reminding ourselves here that all treatment means are the same. That is a special case of each treatment mean is different, or each treatment mean varies linearly or quadratically or anything else. When we say that it's a special case, we mean that it's included in a more complicated model, or perhaps is a restriction. That's a more mathematical term we'd use than that complicated model. Sometimes we say that the special case model is nested in a more complicated model, but I don't like saying it. I like to say it's a restriction of a more complicated model. The reason is we'll talk about nested models later, and so it gets confusing if we use nested in two different ways. So if we have model A, that's a restricted model or included in model B, then model B, by least squares fit, will always fit at least as well as model A, but usually fits a little bit better, okay? The sum of squares for model B cannot be bigger than the sum of squares from A and is usually going to be a bit smaller. Equivalently, the sum of squares for model B, the model sum of squares, is always going to be at least as big, if not larger, than the sum of squares for the restricted model, model A. And the reduction in error of going from A to B is the same as the increase in the model sum of squares going from A to B, because again, it's sum of squares total equals sum of squares model plus sum of squares error or residual. So this partitioning of the sum of squares is what we generally refer to in statistics as analysis of variance, or ANOVA for short. And when we find that the special case model fits as well as the larger model, then we want to stick with the restricted model. But how do we make that decision? Okay, so that's what we're going to talk about next.